Okay, kids and kitties, cats and kitties. This is going to be organic chemistry semester 2. If you can join, great. If you can't, don't worry about it. It will be posted on YouTube under the Chemistry Cowboy site. So go to the Chemistry Cowboy, or I'm going to link this to the Schoology account. So you can join, great. If not, just watch us later and we'll deal with the after facts. As I said, when it comes to quizzes, I will post them online under Schoology, under the quiz, and you should set some way so you can access it up to like 3 hours before this time and 2 hours from like 9 to 3? 9. Yeah, 9 to 3, something like that. So you have a 6-hour window to copy it down, print it off, and whatnot, and solve that. And get it back to me. At that point, it'll become due. That's the best I can do, considering this is what we got to deal with. One thing I would suggest I'm going to share a screen. Actually, I'm going to go back to a whiteboard, but right now I'm going to just share screen. Okay, close that. Close that for now. One thing I would suggest that you download, if you don't already have it, it's a thing called Marvin Sketch. It comes with a couple other programs, including Structure Checker and Marvin View and Marvin Space. But Marvin Sketch is a molecule drawing program that should allow you to do a lot of compounds. And there's a lot of things you can use with this, but depending on which is going to be easier, I might use this to draw my structures, or I might draw by hand on a virtual whiteboard. But so I can use this to oh, hey, I want to draw, here's an amine. This is how I draw all of my test structures, and it's also might make it a lot easier to do some of the homework assignments or some of the formals. So now what we will be doing and talking about today is we'll be starting a new chapter, chapter 18, ketones and aldehydes. So a ketone and aldehyde. So I'm going to go stop screen share and go back to a whiteboard, and that's what I'm going to work for, unless this Marvin Sketch ends up being better. So ketones and aldehydes are compounds with the carbonyl C double bond O group. C double bond O group. Our carbonyl group. A ketone is specifically a C double bond O between two carbon chains, while a aldehyde is a C double bond O between a carbon and a hydrogen. Essentially, aldehyde is a carbonyl group at the end of a carbon chain, and a ketone is at the beginning. But a ketone is somewhere in the middle. Doesn't matter exactly where, just somewhere at not the end. So talking about these bonds to begin with is that if you compare a carbonyl to C double bond O with a C double bond C, we find that these guys are shorter, they're stronger, and they're often more polarizable than the alkenes. And why are they more polarizable? It comes down to this minor contribution resonance structure, where if I look at this, there is a resonance structure. I could draw that, the plus on the carbon, a minus on the oxygen. Now, this is a minor contribution, but it does play a significant part. And if you remember, when we did Grignards, where did the Grignard add? It added to that carbon, that positive carbon, on the carbonyl. As we're going to do a lot of reactions, we're going to have negative attacking that carbon and positive things being attacked by that oxygen because of this minor contributor. So the first thing we need to do is, before we talk about like the reactions, to how do we name these guys? How do we name these guys? So once again, we're changing the ending of our alkane with the E ending. Remember, if we had the alcohol, we remove the E and become alkanol, some sort of like methanol, hexanol. Well, the same thing. We're going to change the ending, and with ketones, we're going to change the E, and it goes to O and E. So it's going to be some sort of alkanone. So like, for example, if I have 1, 2, 3, 4, 5, so this would be 3-pentanone. No. Excuse my shoddy handwriting. I'm drawing this by smudgy fat finger onto a touchscreen. 3-pentanone. We number where it's occurring in the structure. Now with aldehyde, we remove the E once again, but now it becomes Al. And we don't always have to number this, because aldehydes, by definition, needs to come at the end of the chain or at the beginning of the chain. So we're always going to be assumed, or that is like just the same way as nitrile would always come at the end of a chain unless it's a functional group. So we'll call it aldehyde would be alkanal or carbaldehyde of some sort. So if we just did, that's propane, that's a propane, we'd call that propanal. Now, keep in mind, when we consider all of our other functional groups, we got to keep in mind the priority when it comes to naming these guys. When it comes to naming them. So, and this kind of, one way to remember this is it has something to do with our oxidations. How many oxygens? Acids will take priority, followed by esters. But both of these guys have 3 CO bonds. C double bond O and CO, single bond. Then we'll have our aldehydes and our ketones. Aldehydes take precedence because they are always going to be the lowest number, because it's always going to be at the end. And the same thing with acids. Acids are almost always at the end. Esters would be continuing a different chain, which is probably why they're secondary. But those have 2 carbon-oxygen bonds. Then we have their alcohols and amines. They have specifically 1 carbon-oxygen bond or carbon-nitrogen bond. And then finally, we have our double bonds, double and triple. We have our basic alkane, And then we have our ethers and halides. And we typically, halides and what have you. Things like, we don't include our nitriles and like nitro groups and into that for whatever reason. So remember, acids and esters, we won't get to them for a bit. But so if I have an alcohol and an aldehyde, I'm going to name this after the aldehyde more times than not. I'm going to number this so the aldehyde has the lowest number because it has the highest priority. So now, let's see. If these guys are not high priority, like they are a functional group, part of a functional group coming off of there, like ketones is an oxo group, and aldehyde is often formal. Formal. Now, you may see some ketones under the common name. The common name would be named for a ketone is often the two R groups named separately with a ketone at the end. So like, instead of calling that propanone, you might call it methyl-methyl ketone. And if it's, instead of this calling it 2-butanone, you might call it methyl-ethyl ketone. So you might see those, or you might see the Greek name, like acetone is probably a more common way of seeing that dimethyl ketone. And we'll also occasionally see some phenones, some aromatic rings with ketone attached to it. Okay. Okay, so let's do some practice. So let's think about how we would name this. If you're working along, I suggest maybe you pause it now, think about it, come up with a name, and then we'll come out. So let's say, so we have a ketone and a halide. Ketone's going to take preference. So let's see how big the structure is. 1, 2, 3, 4, 5. So it's a pentan 2 pentanone. Now we're going to call it, this is a chloro. Chloro comes at the 4. So 4 chloro. I've already run out of room. 2 pentanone. What might this one be? It's pretty simple. Besides that is an oxygen. Well, we have a 6-membered ring, which is a cyclohexanone. You won't have to number this one because it is implied there's no other functional groups. So that we're going to start counting from the ketone, carbonyl group. Let's see. See. Now, there's two ways you can name this one. One is probably the more common way you're going to see this. Call this, if you think of it as a benzyl group, I'm not sure this one's right, but benzyl. No, probably not, because that'd be confusing with benzyl. You might be able to call it phenyl methanol, but probably one of the more common names would be benzaldehyde. Benzaldehyde, because of the, well, as the aldehyde, it has to be coming off the benzene, but the benzene has no ending point, so it must be physically coming off of the benzene. As we think about that. So let's look at this. So what are the properties of these guys? Now, when we talk about properties of ketones and aldehydes, they have a very large dipole because of this carbonyl bond. So it means they're going to be very polar, but there is no direct hydrogen attachment to the oxygen. So there is not a obvious hydrogen bond. Now, that's not to say they cannot form hydrogen bonds with the solvent. That's not to say there cannot be intramolecular hydrogen bonds if there is an alcohol group somewhat nearby. But as currently stated, they are not guaranteed a hydrogen bond the same way as an alcohol would. So if we're comparing boiling points, alcohol groups have a much greater boiling point than, say, an aldehyde or a ketone. So ethanol is much lower vapor pressure than, say, acetone. Considering acetone weighs a little bit more, but they still have a greater boiling point than, say, an ether, where we don't have a greater polarity difference like we do with the carbonyl. Not as large of a dipole moment. But of course, an alkane has the lowest of all. So this guy's kind of in the middle, somewhere between ether and alcohol. Can't really say exactly, but we know there are, and it's all reasonable boiling point. It's not going to be, we can keep acetone on the table for a while, just know that if you leave it for a couple weeks, it will all evaporate. Now, because of the polarity, ketones and aldehydes are good solvents for alcohols, and they're moderately soluble in water. So these guys will dissolve in our water to some extent. We will often use these guys, if you remember some of the labs, we use these as common solvents. Now, if we're looking at infrared and NMR, these guys, we kind of already talked about them, but we got to hit it again. The infrared, these are very easy to see. These are very easy to determine. In infrared, we have a stretch around 1700, or the carbonyl stretch. So 1700 or a CO stretch. 1700. Now, if you have an aldehyde, you see a CH aldehyde stretch well below what you would expect for sp3 hybridized stretch. So 2710 or 2810, somewhere between there, where the sp3 hybridized usually goes from 3,000 to about 2,800. So these guys will have some distinguishing features just looking at the infrared. And of course, if there's conjugation, that's going to lower this bond strength of these guys and lower the frequency. So if I have like enone, which we're going to talk about in a couple chapters, like ketone, alkene, this conjugation is going to lower this number. It's going to weaken this bond, so it's not going to stretch it high of a number. But of course, ring strain is going to increase that number because it's going to be pulling away. So if I put a 3-membered ring, high ring strain, it's going to make that number jump up. So there's ways to deal with that and see that. Okay. Now, in proton, there's a moderate shift downfield for most CHs alpha to the aldehyde, so or ketone. So if I have this and I have a CH, it's a moderate shift downfield. So it's going to go that way. Not as much as an alcohol, but still it's going to be, you can tell there's a functional group attached there. But one thing you will see is this guy, if you have an aldehyde, you will see a peak at between 9 and 10 ppm. This is because the large electron withdrawing effects of that carbonyl group pulling electron density out of the H, de-shielding it, allowing it to shift way, way downfield. So the only time you'll see a 9 or 10 ppm peak is with usually an aldehyde. Now, with carbon-13, these are also dead giveaways. Aldehydes and ketones both are approximately at 200 ppm now or greater. These are the only things that will come around 200 ppm. Now, there's a way to tell the difference between them on that, but I'm not going to get into that nitty-gritty. But if you have a carbon-13 peak at 200 ppm or greater, you have some sort of carbonyl group. That's a dead giveaway. And carbon-13, they're alpha carbons. So if I have this adjacent, this guy's going to go 30 to 40 ppm downfield. Maybe not as much as, like say, the alcohol, but it's going to shift. So it's going to be pretty obvious. So we're going to skip talking about the mass specs, skip talking about the UV vis, but these guys will absorb the UV vis and be very obvious, but we didn't really go over them. I'm going to probably take a quick break here, and I'm going to rejoin us around 12:30 again. So I will see you in a minute. Welcome back from our little break. If you had a chance to go use the restroom, well, I'm back to it. So continue talking about ketones and aldehydes. So first thing we're going to do is review how do we make them before we talk about other reactions. The first way is really the easiest way, and that's the oxidation. We have oxidation such as the easiest way to make a ketone is to directly oxidize a secondary alcohol. So we have alcohol group, and we do some sort of oxidation. Doesn't matter what, because of the nature of the secondary. There's only one hydrogen that can be removed, so it can only be oxidized one step. So oxidize this. Well, we could do this, remember, with sodium hypochlorite, otherwise known as bleach, common oxidant. Bleach and acetic acid, that is. We could do this with some sort of fuming sulfuric acid and dichromate to form chromic acid. Basically, some really strong oxidant. We talked all about those. Though, we could turn an aldehyde to a ketone, but that's a little bit trickier. And how would you do that? We have to first turn the aldehyde to a secondary alcohol. How would we do that? Well, you'd use Grignard. So let's say we have methyl magnesium bromide, step 1. Gotta make sure this is separate, step 1, and step 2, use acid. Let's recall this. The methyl attacks the oxygen. Welcome. The methyl attacks the oxygen, and we would form a methyl attacks this, the carbon, kicks it up. Step 1. And then step 2, we protonate that to make a secondary alcohol. And of course, we just then oxidize that again. And now we have going from aldehyde to ketone. Welcome, Dalton. Can you hear me? No. I see we have one of my students who's finally joined, and don't worry, you can catch the whole thing when I post the video up on YouTube in a few minutes, and we're all done. We started with the first video talking about how do we name aldehydes and ketones and what are the properties of aldehydes and ketones. So we're just now getting into the basics of what reactions do we have. Nope, back to 1. All right, and we lost him. That's fine. Okay, so now if we back again, we'll see. Give it a minute. See if his internet is as good as I hope. Any luck? Can you hear me? No, yeah. I'm going to keep going, plowing through, and post this video later. Okay, so if we were to take that same oxidative approach to a primary alcohol, remember, primary alcohol would first oxidize to an aldehyde. Hooray! But then, more often than not, it would continue oxidizing because primary alcohol is less reactive than an aldehyde, and it would keep going to a carboxylic acid. So how did we prevent that? We prevented that by different kind of oxidative tamers, ways to temper this reaction. We use that with such solvents, such catalysts like sodium hypochlorite, which are bleach, and our tempo. which was our compound that tempers the oxidation. We've done it with PCC, PCCC. That was a weaker oxidant. And there was a couple others we didn't really talk about, like such as Swern oxidation and DMP. So, but there's ways to limit the oxidation to just ending up with an aldehyde rather than going all the way. So that's the first way is simple oxidation. The second way would be, reminding us back, ozonolysis. We could take a double bond in the presence of first ozone at really low temperatures, ozone at -78 degrees C, and the second step we use our I think reductant. The ozone will break those double bonds and put a bunch of oxygens in there. In fact, 3 oxygens in there. And the oxidant, our dimethyl sulfide, will extract one of those oxygens and form whatever this is cleaved. It's going to cleave that into an aldehyde. And that into a ketone. So that was a way we used to form aldehydes and ketones. And of course, a few more things. There was a few other ways. Let's see. Yeah. One we did Friedel-Crafts acylation. That was one of the most recent ones we talked about, where we took some sort of acid chloride and we had some sort of activated benzene group on there, and in the presence of aluminum trichloride, and then water, we added to the ortho or para position. Assuming, because these needed to be activated. So we added either they're added directly adjacent to that G group, or we added directly opposite. What am I doing? Oh, that's not what I want at all. That was one way we made ketones, but that requires you to already have a ketone or some sort of acid chloride. So that's not super helpful, but it's a way to make phenyl ketones and phenylaldehydes. There's one method we didn't really talk about in class, but there's a way to put an aldehyde onto there using carbon monoxide. It was called Gutterman-Koch. I'll just briefly mention it, but I doubt we'll be going too much into this. The idea is that you take this benzene, presence of carbon monoxide and HCl. Awful. HCl. And the second step involves using the aluminum trichloride and a copper catalyst. Copper chloride. We can add. We're adding a CO and then we're acidifying it with the HCl. But we didn't really go into the mechanism, and we didn't really even go into that reaction. Now, sorry, there's various ways we hydrated alkenes and then oxidized them. Hydrated alkenes and oxidized them. So that ways that we can form these guys. No, sorry, these are hydration of alkynes. Hydration of alkynes. Well, they're using some of the methods we've seen before. We're using the mercuration, demercuration, or hydroboration, oxidation. Those were ways if you had just a standard alkene, you could add alcohol onto it. But we're going to take it one step further. So if we're using an alkyne, so alkyne just like this, we're going to be first forming a alkene-ol, so a double bond with an alcohol, and then we can reduce this with in the presence of acid or base, depending. So there, depending on which method we add, can either be Markovnikov addition, where we add the hydrogen to the side that has more hydrogens, or anti-Markovnikov, where we add it to the opposite side. So let's see. Like if I use mercury and sulfuric acid, H2SO4, acid, we end up getting what, like alkene all, and then in the presence of a proton, this gets oxidized and this gets turned into a methyl. So we get R essentially what we're doing, we're protonating here. The double bond is the proton. Basically, let's see, this would be attacking here. Then a lone pair would be attacking there. And then this proton would be deprotonated to form that compound. Finally, if I did the hydroboration, I did that, the opposite one, anti-Markovnikov. So all these should be reviewed. Step 2, peroxide. We add that on, and then remove that off and oxidize it. We get the anti-Markovnikov. So we got the hydrogen adding to the opposite from expected. And then upon deprotonation, OH, we can form an aldehyde. So we're attacking here. Actually, no, sorry. Erasing that. We're going to attack probably there. Flip up. Sorry. No. See, I'm trying to think about this reasonably. Reasonably, that would have to depronate this, where it would lone pair, then would go down to stabilize that, kicking that over here, and then this is R minus, which can then depronate water to form the CH2. All those are just ways that we've seen in the past, that we've seen in general chemistry 1 or general chemistry, organic chemistry 1 or in the earlier chapters of organic chemistry 2. So here is the first new method of making a making a ketone or aldehyde. So it's making a ketone from a carboxylic acid. So we start with our basic carboxylic acid. And what we're going to do is first we're going to depronate this, and then we're going to attack with a organolithium catalyst. Now, you could have just attacked with organolithium catalyst, but you would have to add 2 equivalents. Because remember, acids are the first thing to go when you attack with a Grignard or organolithium. R minus is a stronger base than the O minus. So we're going to deprotonate that first. So it's just better if we just add, so we don't spend our organolithium. First off, deprotonate this. We have R, C, O minus with a lithium. Then we add our organolithium, and it's going to attack. It's going to attack, kick that up. So now we have our R, O minus isn't very stable. So what we got to do is we're going to protonate this. So we have a diol, geminal diol, but that in itself is also not super stable. So this is actually going to be just a transition state that's going to rearrange itself, dehydrate, and rearrange itself to form. So alcohol is going to attack up here. That's going to shift down there. Dehydrate to form our ketone. Now, as I said, you could do this with 2 equivalents of our organolithium. It just seems a little bit more wasteful because organolithium is going to be more expensive to make than our lithium hydroxide. With the same process, a strong enough base deprotonates that acidic proton. From there, the nucleophile can attack the electrophile, shifting direction up. Then we have 2 strong acids, 2 strong bases meet an acid. Acids get pronated, the bases get pronated. And here's where it gets a little weird, where we have the rearrangement. Doing that, that's where that's where it'll form the ketone, forming water. We'll go over one more example today, and then we'll start, and then I'll wrap up. So, and that's forming ketones and aldehydes from nitriles. Remember, nitriles are C triple bond N. So, the first thing is you can use Grignard or organolithium. Any sort of Grignard or organolithium. So, like, say, we'll just do methyl magnesium chloride. So the first step is it attacks and we form an imine. Forms an imine. So an imine, remember, is a C double bond N. So step 1 and step 2 we pronate. Now from that imine, in the presence of more acid, we will remove that nitrogen and exchange it for an oxygen. Imines are not particularly stable in the presence of acid, so we're going to exchange that and form an ammonia as opposed to hydronium. That is one way, just using a Grignard or organolithium. Let's see. Or we could use a way to transfer of like hydride. So diisobutyl aluminum hydride. This was known as a particularly powerful. This was given as one of the examples of the oxidants. When we said where there's aluminum tetrachloride, we had aluminum tetrachloride. We had not aluminum tetrachloride. We had aluminum, like sodium aluminum hydride, and we had sodium borohydride. We also had this diisobutyl aluminum hydride, or IBU2ALH. These guys are just to make sure to help stabilize this. The hydride is what's actually going to be transferred. This is also abbreviated as dibol-H. So if I do this, what's going to happen? What's going to happen is we're going to transfer a hydrogen. Transfer a hydrogen. There. And that's going to attack the aluminum. And then from there, when we pronate this, once again, kicks off the amine. Imines are not stable. Kicks off the amine because we added a hydrogen instead of an R group. We're left with an aldehyde. So the basic premise of this is something attacks the nitrile, and then we exchange the resulting imine for an oxygen. But that's all I got time for today. I hope this will be informative. I hope this is legible, but we'll see. is that I will post these online shortly under the group, the Chemistry Cowboy on YouTube. So I'll try to I'll see whether it's easier to put them together or keep them separate. Doesn't really matter.